Hello everyone, welcome back to video lecture series on VLSI design. My name is Dr. Prashant Bachanna, working as assistant professor in the Department of Electronics and Communication Engineering at Institute of Aeronautical Engineering, Hyderabad. So in this lecture of video series, in this video lecture, we'll be learning the short channel effects, the CMOS inverter. So let us start our discussion with this topic today. So let us start our discussion with short channel effects in the MOSFET. So we know this is the structure of the MOS. Okay, I'll take a MOS. Okay, so this is source, this is gate, this is a drain. Okay, and this is the substrate. Let us say substrate. So 4 terminal source, gate, drain, and this substrate. So the short channel effects are the effects will happen because of the reduction of the distance, that is length between source and the drain. So because of this, the short channel effects arise in the MOS transistors, either it may be a P-type transistor or N-type transistor. So short channel effects are the effects with short channel effects. Short channel effects are the effects which is done with the if you reduce the length of the distance, if the length between source and drain is reduced. So let us say if it is like this, and if it becomes like this, then the short channel effects occurs. So what are these short channel effects? There are different types of short channel effects are there. So we'll discuss it one by one. That is drain induced barrier lowering, surface scattering, velocity saturation, impact ionization, and hot electron effect. Okay. So we'll discuss these short channel effects one by one. So the first short channel effect that we come across is a drain induced barrier lowering, which is normally pronounced as DIBL. So this happens. So this side effects happens because of the increase in the VD. Okay, if you increase the voltage, it reduces the barrier phase by electrons or the holes in the source, allowing them to go from source to the drain. So the gate loses control of flow of current through MOS. So we'll discuss the working of this short channel effect, that is drain induced barrier lowering, with this diagram. So if VD increases, the electrons, if there is increase in VD, then it reduces the phase of electrons or the holes. So because of this, what will happen is that the electrons, okay, the source allowing them to go from source to the, so there will be a movement of electrons from a source to the gate terminal. So this effect we call it as drain induced barrier lowering. So because of this, what will happen is this is source, this is a drain, this is gate. So this is source, gate, and the drain. So the gate loses the control over the transistor. Okay, so this is gate, this is source, this is drain. So if VD increases to some extent, what will happen? The gate loses the control over the complete transistor. So in the transistor, there are 4 terminals are there: source, gate, and the drain, and the gate act as the control. But if we increase VD, if VD increases, the electrons or hole mobility will decrease. So because of which, what will happen? The electrons of the holes will start traveling from source to the drain. So with this, what will happen? The gate loses the control over the working of the complete transistor. So this effect, what we call it as we call it as drain induced barrier lowering. So we will analyze this DIBL with the help of these two graphs. Let us say on the x-axis we are having gate voltage, on the y-axis the flow of current. Okay, so in the beginning, the gate will have the control over this thing for VG is equals to 1 volt, 2 volt. But at some volt, at some VD, what will happen is that at some voltage, what will happen? The electrons of the holes will start traveling from source to the drain. So with this, what will happen? The gate loses the control, and there will be a variation of the negative current. That is the induction of electrons or holes. So the movement of electrons from. So this is DIBL. So the second diagram will show the DIBL. So this is for the normal ID versus VD characteristics of the MOSFET. But this is when DIBL, drain induced barrier lowering, occurs because of the flow of this flow of electrons of the hole from source to the drain. Electrons, yeah. So the movement of electrons from a source to the gate, which yields to DIBL. That is the electrons will start flowing from source to the drain terminal. So because of which the gate loses the control over this terminal. So this is our first type of the short channel effect, that is DIBL. Now we'll go the second type of the short channel effects, that is surface scattering. So as the name itself indicates, the surface scattering, if the channel length, okay, so in the long channel, what will happen is the EX is greater than EY. So but in the short channel, EX is not negligible. So EX and EY field makes electron to travel in a zigzag path, so reducing their mobility. So as channel length decreases, electric field also increases, so causing surface mobility to become the field dependent. So for the long channels, EX is greater than EY. So what will happen is in the surface scattering, the electrons, if the VGS is greater than the threshold voltage, that is threshold voltage is a voltage at which the transistor is on, or we can say the constant flow of current will happen at threshold voltage. So if the VGS is greater than the threshold voltage, okay, so what will happen is this surface scattering will happen, and the electrons will start moving in the zigzag position. So in the zigzag manner, the electrons will move from source to the drain terminal. So this is the effect of this is the effect of So this is the effect. We'll see in this diagram. See, let us say this is our transistor. Okay, so because of the length, this is source, this is gate, this is drain. So if the length reduces, what will happen? The second effect is the surface scattering. The electrons will start moving in zigzag position. So the surface scattering will occur in the movement of electrons from source to the gate. So this inversion, this layer, we call it as an inversion layer. Which is called as surface scattering. So this is the second short channel effect that will encounter the MOS encounters. For the long channel, EX is always much greater than EY, but for small channels it is negligible. So if EX and EY field makes electron to travel in zigzag position, so this effect we call it as it's a loss to the like these are the problems which are faced by the MOSFET because of the short channel effects. Then the third short channel effect we'll discuss is a velocity saturation. So velocity saturation and it has no effect of increase in the electric field. So what will happen in the velocity saturation is, so if we increase the voltage, okay, if there is an increase in the voltage, as you can see in this graph on the x-axis, okay, x-axis there is an increase in the voltage, and on the y-axis characteristic is shown here. So at some particular voltage, what will happen if we increase the voltage also, the current, okay, so this is current, so the current flow will become constant. Okay, so this voltage we call it as saturation voltage. So the velocity saturation happens at V saturation, that is saturation voltage. So saturation voltage, we can define it as a voltage at which if there is increase in the input voltage also, the current flow will become constant. So this effect we call it as the velocity saturation. So this was about the velocity saturation. Then the next short channel effect that we'll discuss is the impact ionization. So in the impact ionization, as the name itself indicates, the electron traveling to the drain creates electron hole pair by impact ionization. Okay, so when electron is traveling, when the electron is traveling, okay, so this is source, this is gate, and this is the drain terminal. So the electron traveling to the drain, okay, so the electron traveling from source to the drain, okay, so creates an electron hole pair, that is electron and hole pair. Okay, so this creates in impact ionization, and the secondary electrons are collected at drain, causing the current to increase in the saturation. So because of this, what will happen? The current to increase in the saturation region, and secondary holes are collected at the substrate using so because of this phenomena, what will happen is, because of this phenomenon, okay, so this is source, this is gate terminal, this is drain terminal. So because of this impact ionization, the electrons will be collected at the drain region, and the holes is created at the P substrate. Let us see if it is an NMOS transistor. Okay, so this is substrate region. So this is also one of the short channel effect, that is impact ionization. So it makes electron hole pair, and the electrons are collected at the drain, and the holes are collected at the substrate. So we know there are four terminals: source, gate, drain, and the substrate. So because of the impact ionizations, the holes get collected at the substrate region. So this effect we call it as impact ionization. Then the final short channel effect is called as the hot electron effect. When VDS is high, the electrons near the gate will receive high kinetic energy, and some of these electrons might be tapped into the gate oxide, so which may damage the gate oxide or the threshold voltage. So this effect, what we call it as hot electron effect. So the hot electron effect, in the sense, it's a transistor. This is source, this is drain, this is, let us say, suppose gate, and this is our substrate. Okay, so if the voltage VDS is high, okay, so the electron near the gate terminal, whatever the electrons are there here, okay, so they will go into, if VD increases, so these electrons will go into the oxide. So this is our silicon dioxide layer. Okay, so if there is an increase in the threshold voltage, if there is increase in the VD, it will increase the threshold voltage. Then what will happen is that some of the electrons will move into the this silicon dioxide. So this effect we call it as hot electron effect, the damage done by the these hot electrons into the transistor. So this reduces the flow of current from this. So after this, if some electrons are moving into this oxide region, means obviously the current flowing from the source to the drain, okay, so will also reduces. So this effect we call it as hot electron effect. So hot electron effect is the effect if there is increase in the VDS, that is drain to the source voltage. So some of the electrons will move into the silicon dioxide. So because of that, so obviously there will be a reduction of current, that is flow of reduction of current from source to the drain, so which reduces the input impedance also. So if there is an decrease in the currents in the sense, so this will reduce the impedance. Then this leads to the deposition of negative charges on the gate, which leads to an increase in the threshold voltage by increasing the flat and the flat band voltage. So the effect of this, what will happen is that the electrons are accumulated here. So because of the accumulation, the VD, the threshold voltage will also increases. So this degrades the MOSFET characteristics like the gate. So because of this hot electron effect, so some of the MOS parameters like the gain and all will be reduced. So this is one of the all the short channels what we are discussing is because of the reduction of the length between source and drain. So if it reaches to some effect, so it is having some of the these side effects, these damages to which will occur to the MOSFET. So with the reduction of the distance between the source and the drain terminal, so the hot electron effect, the electrons get accumulated near the silicon dioxide layer, so which will have an impact on the some of the MOS characteristics like gain and other factors. So this concept we call it as hot electron effect. So you can see the same thing here. So the hot electrons, as you can see here, this is source terminal, this is gate, this is drain. Okay, so the hot electrons get accumulated near the silicon dioxide layer. So because of this, the current flowing, see the current was flowing. So the current flowing in the from source to the drain will also decrease. So which will impact the threshold voltage here, which will in turn increase the threshold voltage. Okay, so the technique used in floating gate devices to increase the threshold by trapping the electron in the floating gate. So this we can use, this hot electron effect can be used here, and to reduce hot electron effect, the drain is lightly doped, resulting in less electric field created for the carrier. So because of this, to avoid this hot electron effect, we'll pole some the drain is lightly doped. CMOS inverter. CMOS stands for complementary metal oxide semiconductor device, which is generally pronounced as a CMOS. CMOS is a type of MOSFET. So in the previous video lectures, we have seen the working of the MOSFET. There are two types of MOSFETs. We have seen N-type and P-type, and the third type of the MOSFET is a CMOS. It is called as complementary metal oxide semiconductor. So where its fabrication process uses complementary and symmetric P-type and N-type MOSFET. So we can say the CMOS transistor is made up of two symmetrical P-type and N-type MOSFETs pair for logic functions. The main CMOS devices characteristics are consumption of low static power and high noise immunity. These CMOS inverter acts as a basic building block for many of complex circuitry. So the purpose of studying the CMOS inverter is that the CMOS inverter is used to construct complex combinational and sequential circuits to design a complex system. So this CMOS inverter is the basic building block. So on a single chip, the input variables as like the basic, the CMOS inverter is nothing but a basic inverter circuit which is used to accomplish a logic variable by complementing A to A dash. So as the name itself, it is indicating the CMOS inverter. The CMOS inverter has only one terminal. So if we give input 0, the output will be 1. And if our input is 1, the output will be 0. So this is a basic functioning of the CMOS inverter. And this is the diagram, circuit diagram for the CMOS inverter. And this is a truth table. If input is 1, the output is 0, and vice versa. And this circuit shows the circuit diagram of, this is the symbol of CMOS inverter, this is symbol, and this is the circuit of, you can say, the circuit diagram of the CMOS inverter. As you can see, this is a P-type transistor. A CMOS consists of P-type transistor in series with N-type transistor, and both the gates of both the gates of both the P and N type are shorted, and it is given as input, and the drains are given with the VDD here, and the output is Q from here by shorting these two terminals, source terminals. So this is the normal functioning of this. So so the CMOS inverter is used to complement a number from A to A, that is 0 to 1, and vice versa. CMOS inverter is a very simple circuit. It's designed with two opposite polarity of MOSFETs with the complementary way. So the CMOS inverter definition, what if you want to see, is a device that is used to generate logical functions, which is known as CMOS inverter, and is essential complement in all integrated circuits. A CMOS inverter is a FET basically. It's a type of field effect transistor which is composed of metal gate that lies on top of oxygen insulating layer on a top of semiconductor. So these inverters are used in most of the electronic devices which are accountable for generating data in the small circuits. So this is the symbol of this. This is the circuit diagram. So the logic elements what we have seen in the diagram, okay, so is applied, it is having one input. So in digital logic circuits, binary arithmetic or switching or logic functions, mathematical manipulations are best performed through the symbols from 0 to 1. So since we use input as 0 and 1, so all these will be benefiting in developing these circuits. So if the input is 0, the output is 1, and vice versa, as I discussed earlier. So this is circuit diagram, the complete circuit diagram of the CMOS inverter, as you can see in the diagram. So this is a P-type transistor, this is a N-type transistor. So this we have done with the help of this dot. So if there is a bubble in the gate terminal, is a PMOS, and if there is no bubble, this is NMOS. Okay, so the gate of both these are in the CMOS inverter. A P-type transistor is connected in series with an N-type transistor. The gates of both the P and NMOS are shorted and is given as V input. That is the first input of the CMOS inverter. And the drain terminals are connected to the VDD, and this from this point, by shorting these two terminals, we will be taking the output. So the source, gate, and and here we can see the source and the drain terminals can be interchanged. If they are interchanged, we have to see what is the effect. Okay, so that was like if we interchange, then there will be some of the. So here a P-type transistor is connected in series with the N-type transistor. Okay, so the same thing whatever I explained, the NMOS transistor is connected at the drain, and the gate terminals, voltage of VDD is connected to the source, as you can see in the figure, and the GND is, that is the ground is connected to the source of NMOS. CMOS inverter utilizes PMOS and NMOS transistors, so controlled by an input voltage. When a low input is applied, the PMOS transistor is on, and vice versa. So as you can see here, so when the input is 1, so we'll see the working of the CMOS inverter in terms of these gates. Let us say the input is 0, what will happen? So the CMOS inverter will take only one input. If the input is 1, the output should be 1, and if input is 1, the output should be 0. So let us say in the first case, the input is 0. So the input is 0, the PMOS transistor is on. So this is on, and NMOS transistor is off. Why? Because in the PMOS, the majority carriers are the holes, but in NMOS, the majority carriers are electrons. So because of this, what will happen? The PMOS is on and NMOS is off. So since NMOS is off, it is connected to the ground. Okay, so this is off. Okay, then this is on. So this is on means whatever VDD is there, we will get the output as 1. See, the input is 0, I am getting output 1. And if the input is 1, okay, so the current flows here, and here is the output. Let us say the input is 1, then what will happen? If the input is 1, so in that case, what will happen is the P transistor is off here, because majority carriers are the holes here, and the NMOS transistor is on. So the current start flowing from VDD to here. Okay, from here when you give input voltage, the current start flows, but since it is connected to the ground, so all the current will be given to the ground. So what will happen, even though if it is on, the output voltage will be 0. So in these two things, we have learned that if the input is 0, PMOS is on and NMOS is off. Since PMOS, the current is flowing and we get the output 1. Whereas in case of the second case, the NMOS, even if it is on, it is to the ground, the current will be drained off. So this is the working of the CMOS inverter. The same thing, the quality of the CMOS inverter is accessed using the voltage transfer, that is the VTC characteristics of the CMOS inverter can be best understood by the help of this graph, wherein we have drawn a graph of input voltage versus the output voltage, that is V in versus V out. So this curve provides an insight into the crucial parameters like gain, logic levels and noise immunity. So as you can see, for different gate, the input voltages from 0, 1, 2, 3, 4. So at some saturation point, let us say the saturation point is here. So at saturation point, the current flowing, okay, at the saturation point, the current flowing will become. So this is the characteristics, and this will affect the flow, the flow of current in the transistor. So in ID, VTC resembles in an inverted step function. That is, in the beginning, it will be on and off. So this shows that thing. That is, the VTC characteristic shows on and off of this transistor. So the real devices exhibits a gradual transition region. The slope of this region signifies the inverter quality. A steeper soles imply more precise switching. Noise immunity is determined by the input voltage range that produces a stable output on either on state or the off state. Okay, so as you can see, the inverter dynamic characteristics. So there are, like, we have seen the static characteristics. Now we'll see the dynamic characteristics of this. So the dynamic characteristics are rise time, fall time, and edge rate. So this can be easily understood with the help of these two characteristics. So here you can see. Okay, so the rise time, let us say, rise time is TR, right? So the rise time is TR. The graph is drawn here. So in the TR, we will be having the time taken for the output signal to fall from 90% to the 10%. So first we will see the rise time. So the rise time TR is the time taken for the output signal to rise from 10 to 100%. As you can see in this figure here. Okay. So see, this is rise time. So the rise time is the time required, okay, to increase the voltage. So fall time is the time required to fall the voltage from 90 to 10%, and here in the rise 10 to 90. So this is called as TR. And the fall time, the time taken for the output to fall from 90 to 10%. So this is our fall time. So the fall time and the rise time. Okay, so these two are mentioned here, and we have one more character, that is edge rate, TRF, the average rise time or fall time. So average rise time and fall time is determined with the help of this rise time and the fall. So these are called as the dynamic characteristics of the CMOS inverter. Okay, so this was the working of this one. That is the working of the CMOS static characteristics and the dynamic characteristics. So we have seen in the today's class, we have seen the working of the CMOS inverter. I'll quickly revise it. This is the symbol of the CMOS inverter. Inverter is having only one input. The input is 0, the output will be 1, and vice versa. This is a truth table. This is the CMOS inverter. And the circuit diagram of this CMOS inverter is shown here. So, the CMOS inverter consists of two transistors. That is, a P-type transistor is connected in series with the N-type transistor. The gates of both the transistors are shorted and is taken as one input, that is input voltage, and these two terminals are shorted and is taken as the output. And VDD is connected to the drain is connected to the VDD. So if the input is 0, the P transistor is on, and N transistor is off. Why P transistors are on? Because in the P type transistor, the majority carriers are the holes, and in the NMOS transistors, since electrons are the majority carriers, so the P transistor will be on and N transistor will be off. So the current will flow from VDD to this output, and we can say that the output is 1 because the output will produce VDD. So there will be a flow of current from source to the drain terminal, right? So after this, if the input is 1, in that case what will happen is, so if the input is 1, the P transistor will be off because majority carriers in the PMOS are the holes, and since it is 1, the NMOS transistor is on. Okay, so since PMOS transistor is off, VDD is 0 here, and even though this transistor is on for some time, the current since it is connected to the ground, so this transistor will be, even though it is on, the current will be drained to the ground, so the output will be 0. So the CMOS inverter is the basic building block for constructing complex VLSI circuits, and this is what the working of the CMOS inverter. The input is 0, the output will be 1, and vice versa. And after that, we have seen the static characteristics of the CMOS inverter on the and these parameters will put a crucial impact on the gain, logic levels, and the noise immunity. And we have seen the dynamic characteristics. In this, we have seen the rise time and the fall time, and the average rise time and fall time. So the rise time is what? The rise time is the time required to increase the voltage from 10 to the 90%. So this is called as tau R, that is rise time. So rise time is the time required to increase the voltage from 10 to the 90%. Then the fall time, as the name itself it is indicating, from 90% to the 10% voltage fall. So which we call it as the fall time of the fall time. So these are called as the dynamic characteristics of these CMOS inverter. So this is about for today's lectures, and these are the references which are used for the preparation of this video. Thank you very much for this opportunity.
Like, share and subscribe. Hit the bell icon for more updates.